morning.
Good morning. Good morning.
I think one of the biggest things in the design space right now is actually what's small. What's really, really small. As a molecular biologist and a geneticist, I'm trained to think at the nanoscale. This is stuff that's invisible, almost no one ever gets to see. But it's becoming accessible now as a design space. Let me give you a quick introduction. These are virus particles. You can't see them with the naked eye. You can't see them with a light microscope. It takes an electron microscope. They're about 30 nanometers across. This is a bacterial cell, an E. coli. It's actually been crushed. That's its genetic material that's been squished out of it. There's about enough genetic material there to encode a high-resolution photograph, about 5 megabits. And that's enough to actually run the operating system of a single cell. The human genome is pretty similar. It's made of the same stuff, DNA, but in a much more compacted form. These are human chromosomes. There's about 6 gigabits of information here. You know, typical small flash drive, except it's thousands of times smaller. You can actually encode so much information in DNA, people are looking at it as long-term storage media. Let me give you a quick introduction by kind of going with the powers of 10. Start with a coffee bean, sesame seed, now a grain of salt. That's about the limits of what you can see. Then you start zooming in to the level of cells, human egg, sperm. Keep zooming in a little bit more. Now you're starting to see some of the structures I was showing you, the chromosomes, E. coli bacteria, baker's yeast, bread and beer. Go in a little bit further. Now you're getting down to the nanoscale. Now you're looking at these virus particles, multiple different sizes. These are essentially software. And now you get down to the very fundamentals of cellular life, the machinery that runs inside of every single cell and connects us all together. Life is one of the most powerful machines. And it operates almost at the same scale as the most sophisticated processors that Intel makes today, about 22 nanometers and less. And yet it self-assembles and has a programming language of DNA. I work for Autodesk. It's a design software company. I'm probably the first genetic scientist they ever hired, maybe the last. But they've given me some really powerful new tools to introduce genetic engineering to new audiences and people. Autodesk has been around for a long time. They work in many different sectors. To show a little bit of a show reel, they create all these different software products that allow you to visualize and simulate and play in design spaces. When I saw this, I thought, wow, I want this in life science. We have nothing like this that allows us to visualize these really tiny things. And the company's been changing because, we used to cater to these really high-end customers, we still do, but what we've learned is that the software has become so powerful today and computing so cheap that you can give people a tablet and really inexpensive software and 3D printers, and now you have a whole new generation of makers. Design has become democratized. Creation has become democratized. So how do we end up tapping into that creative energy to really, change the world? I work with a group called Bio-Nano Programmable Matter. Bio-Nano, I think most people kind of wrap their heads around. Programmable matter is the conversation starter. It's really, all matter is programmable. But it really is, at this level, part and parcel of the design process. And this group didn't exist 3 years ago. It's brand new. And it's because we recognize that this is becoming a design space now. How do we open it up? How do we get new ideas coming into this world and give people a chance to explore? This is just some screenshots of a platform we've been creating called Project Cyborg. Cyborg, cybernetic organism, really the non-living and the living coming together to make something greater. We don't know how to make all the different software in this, so we put together a computing platform that allows the awesome visualization that Autodesk is so well known for. Some of the physics, because it's really weird when you get down to the molecular level, to make some of these things work together better. So you can start to do things like molecular design, and then lots and lots of computing, because it takes some pretty heavy-duty algorithmic number crunching to do things like protein folding and look at docking of different things. So now we actually have a lens to do metabolic engineering, molecular engineering, and we don't want to make this just for big pharmaceutical companies. We've taken a page out of what we've been learning with the consumer space and just making it run on browsers, and trying to get essentially everyone that's a maker, to come into the space and start to explore it. And it's a safe container. And what's really powerful for me in this is it's not just all theoretical biology. You can actually connect these software tools to printers. 30 years ago, desktop publishing was revolutionized because we got the 2D printer. Now we have the 3D printer, and we're still exploring all the amazing creative spaces that are opening up because of this one device. But I want to introduce you to a couple of other printers that I think are really, really powerful. And one of them is the 3D printer that actually prints cells. It's a bioprinter. It's very similar to a traditional 3D printer. It's basically just moving a head around, but in this head, it's not plastic, it's not metal. It is actually living cells, and they can have multiple different types. So this company that does this is called Organovo. We started making software with them to help drive some of their printers, but Organovo is trying to make tissues right now that can do some really remarkable things. They're printing all the cells in a human liver into 3D structures that grow quite thick. And just all those cells working together makes a much more realistic representation of a human liver than we've ever had before in drug development. So companies are able to look for drugs that they've got in development that might end up being toxic to humans much earlier. So the drugs are failing faster. They're able to do much better selective evolution of their products. This is really big. But Organovo is setting their sights on something much bigger. They want to be able to eventually print whole organs, which would be terrific if you needed a new heart or a set of lungs. And there's no reason why you can't do this. You can make unlimited numbers of cells. It's really a factor for printers and understanding how these things are working together. But they scale. The printer that I work with is actually a 3D printer for the DNA molecule. It's truly a nano printer. And we've never had this technology at scale in the past. You send an email file with a DNA sequence, the company will send you back the actual DNA, the physical DNA. This is really remarkable stuff. Most people don't even know it exists. Now, it's not a desktop device you can have sitting in your lab today. You have to go through these companies like Gen9. Send them a sequence, they'll send it back to you. They're really fast, they're really efficient, and they're getting better all the time, just like Moore's Law, which is absolutely remarkable. And what this does is it opens up the possibility of creating some really new, amazing things. This is Sean Douglas, one of the people that is exploring this space. He makes molecular nanorobots designed with CAD software that can do remarkable things. This one is a cancer drug. In the closed configuration that you see down at the bottom, it's inert. It doesn't do anything. But if it binds to a cancer cell, it opens up like a cell phone. And inside, those little pink proteins will kill the cell. So highly targeted, highly selective, super inexpensive to make, completely programmable. This could be a real game changer for many different types of cancers, antibiotics, etc. We're just learning how to explore this space. In fact, and because DNA is actually a programming language for living things, the more we can write DNA, the faster we can do it, the better we get at it. We actually open up a whole new branch to the tree of life. It's a whole new design branch, and people are starting to explore it. Not just scientists, artists. It's accessible to just about anyone in the same way that 3D printing was. Over 20,000 students have been through an international program run by MIT just to train people in this. It's been going on for 10 years. It's called synthetic biology. Probably the most remarkable achievement to date is the actual creation of a synthetic bacterium. The entire genome is programmed, booted up, and a small bacterium now lives on the planet, the first human-designed organism. And the thing is, yes, it took a top scientist to do that, and no one's actually repeated it today because it's just too expensive to print the DNA. But again, in a few years down the road, people will do this more and more. We're already starting to make synthetic yeast about 10 times more complicated than genomically than the bacteria, and much easier for people to work with because yeast, bread, beer, it's a great distribution system. After that, I don't know where it goes. Plants, animals, it's all a function of how cheaply we can make DNA and program it well. But the reality is today, we can't print a lot of DNA. You can't make these giant genomes, so you have to kind of start from the smallest, bottom up, and work with it. This is a little virus called Phi-X174. Phi-X only infects the E. coli bacteria. It's completely harmless to humans. But what's super cool with this little agent is that you can see it when you have this design software. You can really just get a sense of what it is and how it's a molecular jigsaw puzzle that comes together. It's not just a grainy electron micrograph. You can see every protein, and you can build software that pulls it all apart and allows you to manipulate it. Or you can 3D print it and actually hold it in your hands and get a sense for it. Become a friend with it. This was actually made synthetically a decade ago, which is kind of remarkable. It was a big achievement at the time. But today, just about anyone can access these tools and technologies and make the real thing. You can print up the genome of this virus. It's 5,386 bits, like keys, letters, nothing. Today, it's fairly expensive to make, about $1,000, but I guarantee in the next few years, it will be $100 or $10 or maybe $1, which is really powerful, the ability to 3D print viruses. And if you boot it up, this is what it looks like. All it does is kill a few bacterial cells and leave a little clearing. But the same technology, the same tools, can be used to do virtually anything and much more powerful things. This is Philip Dormitzer. He works with Novartis. He was able to show last year that you can get a new flu popping up in China, have it sequenced in China, the sequence emailed to his company. They can actually synthesize a new virus vaccine in less than 4 days, specific to that new flu, and get it into production, saving literally months of time in getting a new vaccine, into production for the world. This changes epidemiology in some radical ways. And this was the biggest innovation in vaccine development in over 30 years. I'm exploring how we might be able to do similar things with cancer. We've been making viruses that hunt down cancer cells now for decades. And it's actually one of the coolest areas of oncology. But I want to see a whole virtual pathway where we can go from sequencing a cancer cell to algorithmically designing a cancer-fighting virus and 3D printing it in days for a few dollars. Not only does this allow the possibility of making safe, effective, and inexpensive personalized medicines for cancer that shouldn't be non-toxic, but because you're making them for one person at a time, you might also be able to leapfrog the years of phased clinical trial testing that a mass market drug today has to go through. All that time, all that money, just so you can sell it to a larger market, which really it may not even help. This is a real revolution in the way we think about drugs, the way we think about drug making, and the idea of making an almost unlimited number of magic bullets, so to speak, for things like cancer, for things like infection, or even things like gene therapies, for rare diseases where a medicine will never be made, except by using these really cheap tools where people can collaborate. This is absolutely a game changer. Pharma's starting to wake up to it. And I think it's kind of cool that Autodesk may be at the very center of the next generation drug industry, or your children, or you if you choose to explore this design space. Because we don't know how big this design space is. Nature has created billions of organisms. We coexist with them. And I think this is an opportunity now for us to revisit life as a design space and figure out how we move forward in a sustainable way to create a living world that we can share with the other creatures. Thank you so much.